Okay, here we're looking at the second cubed roots exercise in Khan Academy. Now, these problems have a real extreme range in their complexity and a real range in how intimidating they appear. Like this one right here doesn't seem so bad, but you'll see others that really feel overwhelming. You might start on a problem like this. It's really manageable. But if you start on one that seems a little ridiculous, hang in there. You'll find a way to break it down, and I'll show you a couple of those here. All right, so the cubed root of 80. The key again to all of this is to use prime factorization. That's kind of our go-to algorithm here to figure out how to break these cube roots down into their perfect cubed roots. So the cube root of 80, I just pick two factors of it, and I'll just pick 2 times 40. Now this is a prime factorization, so 2 is done, that's prime, and 40 can be broken down to 5 times 8. 5 is prime, we're done with that. And 8 is 2 times 4, right? And then 4 is 2 times 2. Now what this does is it breaks the number down 80 into all of its prime factors. So 2 times 2 times 2 times 5 times 2 equals 80. And when we look at these prime roots, every time we see 3 of a kind, we see triplets like this right here, that's a perfect cube, right? That's 2 times 2 times 2, or 8. And the cubed root of 8 is what? Well, that's 2, because 2 times 2 times 2, or these 3 2's, gives you 8. So whenever you do this, you're always looking for a way to clump or group the prime factors into triplets. And you might write it out to keep track of it like this. You might write that the cubed root of 80, if we rewrite that, we can think of it as the cubed root of these factors. I'm just going to change the order. So we have 2 times 2 times 2, right? This is just rewriting 80 to its factors. That's our perfect cube right there. Times what's left over, 5 times 2. So 5 times 2 can't be broken down anymore. Once you've reached that prime state, you're in its most primal form. So here 5 times 2 is 10, and 2 times 2 times 2 is 8. So really we're breaking 80 down into the cubed root of 8 times 10. And that, you can use the laws of exponents here to split it. You won't change the value. Take the cubed root of each factor. The factors are 8 and 10. The cubed root of 8 we just said is 2, and the cubed root of 10 can't be broken down. So that would be your answer here. You'd plug in 2 times the cubed root of 8. So just to recap, our main go-to here is to use prime factorization. But there are other examples that seem a lot more intimidating. We'll do 2 more. Okay, so clear this off. What if I gave you the cubed root of 135? Well, before with 80, 80 was even, we can always use 2. In a lot of these other examples, you'll be able to use 5. If it ends in 5, you know 5 is a factor of the number. So here we have 5 times what? Remember, 5 times 20 is 100, right? 5 times 20 is 100. And we're trying to get 135, okay? So 5 times 20 gets you 100. We're trying to get 135. There's 35 more. I know 5 times 7 equals 35. Together, that's 135, right? So 5 times 20 and 7, or 27, gives you 135. 27 is not prime. Break that down. 3 times 9 is 27, and 9 is 3 times 3. Now what we've just done, like before, we rewritten 135, so it's 3 times 3 times 3 times 5. That gives you 135. Here are your triplets right here. Right? That's your perfect cube right there. And we can rewrite this. Cubed root of 135 equals 3 times 3 times 3 times what's left over, 5. Then, right, we split this up, so it's a cubed root of 3 times 3 times 3, or 27, times cubed root of 5. You can almost see it. The cubed root of 27 is 3. It's right here. 3 times 3 times 3. The cubed root of that is just 3. So the cubed root of 27 is also 3, times cubed root of 5. That would be your answer. More, I guess, there's all kinds of different examples, but here's a real nasty looking one. But we can still manage this. It says 2,187. So here, it doesn't end, it's not even. right? So it doesn't end in a 0, 2, 4, 6, or 8. And it's not a multiple of 5. It doesn't end in a 0 or 5. And it's in a 7. So one other super easy thing to check is to add up the digits. If they add up to a multiple of 9, then 9 goes into the number. So here, since 2 plus 1 plus 8 plus 7 equals 3 plus 15, or 18, and 18 is a multiple of 9, that means 9 will go into this number. So we'll find a way to break it down with 9. So, I actually don't even do the long division, I guess. I kind of just approach it with multiplication. Because I know that 9 times 200 gets me really close to this number, because 9 times 2 is 18. 9 times 200 is 1800. And then we're almost there. We have 387 left over, all right? Because we need to get to 2,187. So I can break that down as well. How many times does 9 go into 347? So what's 347 divided by 9? Well, again, I guess it's not the most efficient way, but it's really how I like to approach this kind of problem. I know that 9, oops, sorry, not 347, 387. 9 times 4 is 36. So 9 times 40 is 360. We're trying to get 387. I have 27 more to go. And to get 27 more, I just do 9 times 3. All right? So altogether, I multiply 9 by 3 and 40, right, to get 387, right? So we have 200 here, and 40 and 3, so 243. Now again, we would end up with another number here, but 4 plus 3 plus 2 is 9. So that means that 9 goes into this as well. How many times? Well, I know 240 is kind of like close to 210, or pretty close to 270. I like 270 because 9 times 30, or 9 times 3 is 27, 9 times 30 is 270. And this 270 minus 243, what's that? Well, it's 27. So this is 27 less than 270. How does that help us? Well, that means it's 3 nines less than 270. So 9 times 30 is 270, 3 nines less is 27. Right? So 9 times 27 is 243. You can test that out. And then lastly, 27 is 9 times 3. All right, now, we're looking for prime factorization. So let me just say, first of all here, because you have these, when it's set up like this, when you have these triplets right here, 9 times 9 times 9, and there's just a 3 left over, you can pretty much stop because you have the cubed root now of 9 times 9 times 9 times the cubed root of 3. The cubed root of 9 times 9 times 9 is just going to be 9. The cubed root of 3 is just the cubed root of 3. We don't know what that is, and you're done. But you could break it down to the prime factorization to see this as well. Each of these 9s is going to be 3 times 3, right? That's 3. Okay. So now, and if we did it this way, every triplet, these 3s and these 3 3s represent 2 perfect cubes. So we can just work with that. That would be the cubed root of 3 to the third, or 3 times 3 times 3. This is all being multiplied times the cubed root of 3 to the third again times 3. Times the cubed root of 3, sorry. Just breaking it down a different way. And the cubed root of 3 to the third is just 3. Because, if you think about what this is representing, cubed root of 3 to the third means the cubed root of 3 times 3 times 3. And that's just the cubed root of 27. And the cubed root of 27 is 3 because 3 times 3 times 3 is 27. And so it's 3 times the cubed root of 3 to the third, which is 3, times the cubed root of 3, which we don't know. So you have 3 times 3, which is 9, times the cubed root of 3, same answer. So that's pretty much as difficult as it gets. And the goal is just to break it down into its factors, and you look for these triplets here. And those are so useful because you're finding the cubed root of a triplet, and that's a perfect cube. The cubed root of 4 times 4 times 4 is what? That's just 4. The cubed root of 5 times 5 times 5 is just 5. The cubed root of any number a times a times a is just a. Kind of like the square root of a number squared is just that number as well. These are inverses. You're cubing the cubed root. It's a nice connection into some of the, I could think, higher intuition with exponents. Thanks.